Thank you, Lydéric, and it's really a pleasure to give a talk on a symposium where trailblazers in the field really made our life easier as a followers. So my talk has two parts. So in my first part, I will discuss some of the activities that we do a little bit longer in the lab, and they revolve around the idea that we start to enter in a field where we combine optics with the fluidics and using a 2D materials. In the second part of the talk, I will focus on a little bit newer results and new territory for us, where we use also a novel nanofluidic architectures to build ionic logic circuits. Starting with the definition of nanofluidics and where we position ourselves. So we position ourselves in my group particularly works mostly with solid state platforms, and these platforms really provide so far different types of geometrical confinement for ions, molecules, and water. The two-dimensional materials and the pores in the two-dimensional materials provide a zero-order confinement, nanotubes, 1D confinement, and Armstrong scale slits also provide a two-dimensional confinement. In my lab, mostly we deal with the 2D materials, hexagonal boron nitride or molybdenum disulfide. And for this talk, I have concentrated mostly on use of hexagonal boron nitride and its optical properties, which would hopefully in the future reveal some of the interesting phenomena that occur in these confinements and as well at the different scales. What we have been learning from these different geometries and the confinements of the molecules, ions, and the water in such a confinements is that we are basically still in a kind of a dark ages, and that we would need some sort of a microscope that would allow us to peer in these confinements and not only rely on current voltage characteristics, either being in a DC or in an AC domain. What we learn about these molecular confinements is mostly from the electron microscopy field. So we have this nice electron microscopy micrographs that allows us to see the devices, but we see them before they have been placed in aqueous solution and before they have been interacting with ions or molecules. Really, there is a large need to kind of combine the two fields, so nanofluidics and optics. In my lab, we wanted to explore the walls of 2D materials as a new kind of a probe to really peer inside these confinements. Again, in the lab, we come across hexagonal boron nitride using first electron microscopy imaging and observing for the first time these defects in context of maybe using the hexagonal boron nitride for nanopore sensing. But very quickly, we have seen that we can maybe use an optical methods to also probe these defects and bridge the gap that is between transmission electron microscopy and optical microscopy using super resolution microscopy. So in the TM, as we have seen, we have very nice high resolution and we can visualize those defects exceptionally nicely. In scanning tunneling microscopy is the same story. However, we are focusing in with those methods only at the small areas. And we would like to have something that is a high throughput and that is also a non-invasive and that it operates at a liquid. So optical microscopy, as we see, can operate in the liquids and also can image 2D materials. However, until we have stumbled on the blinking of the hexagonal boron nitride, the optical microscopy was not suitable for imaging such defects because it lacked the resolution. With Jean Comte and Jean Dongfeng, we have established a method first to spatially distinguish those defects, and Jean Comte implemented spectral channel in our regular localization microscope. So in localization microscopy, we need to have fluorophores that, or in this case, defects that interact with environment and that can change their fluorescent states from on and off in a stochastic way, so that in a diffraction limited spot, we can localize them one by one. And then using these two channels, we can separate their information about location and information about their spectral signatures or energies. So this is what Jean and Jean Dong have been establishing. And what we have seen is that on CVD grown hexagonal boron nitride or on exfoliate hexagonal boron nitride that has been treated with the plasma. So here we have been basically introducing the defects by harsh treatments of these materials, exposing them to oxygen plasma for a short period of time, and then immersing them in water. So in this environment, these defects that have been engineered, not at the locations that we would like, but stochastically, interacted with the environment. And here we believe that they interacted with the proton, changing their locally the band gap of hexagonal boron nitride, and through the interaction we could establish a blinking and as well localization, and further on as well spectral characterization of those type of defects. So we can then characterize a CVD or the CVD grown hexagonal boron nitride in the same way, or this nice hexagonal boron nitride that has been exfoliated and treated with the plasma. So we have now tools to spatially address the location of the defects, that we read their spectral signatures, and that also we have information about their temporal behavior. Interestingly, in that same study, so we have also observed kind of a motion, and we could track a hopping of likely protons interacting with the defect species, and established that these trajectories correspond to directly correspond to the excess protons diffusing along the surface rather than diffusing back to the bulk. So this was all nice, and with this non-deterministically placed defects, we have been a bit frustrated, and we wanted to make our initial motivation was, can we engineer locations of the defects so that maybe in the future we can also engineer conduits or some sort of confinements in terms of channels, or confinements in terms of the holes, which would be then also optically active. But for this particular problem, having deterministically defined arrays of the defects would maybe be beneficial in order to study this hopping behavior that we see on these materials. So we started first by using ion beam, xenon ion beam, writing initially this kind of a checkboard patterns, hoping that if we move down in the spacing of these patterns, we can reach the hopping length that we have been observed in this stochastically induced defects in hexagonal boron nitride. So the main motivation was that from such random trajectories, maybe if we can direct the motion and somehow influence the motion of the hopping proton on the interface of the hexagonal boron nitride. So this was attempted by Evgeny Glushkov, and again, using a systematic study, we started with this xenon ion FIB milling, and basically again using our microscope, we were able to examine the doses. The doses. So in these images, we see non-diffraction limited. So we see diffraction limited images, and also the frames that have been taken for our analysis that will further be used for reconstruction of super resolution images. And the lines that we see here are not resolvable in a regular microscope, but these lines are not full lines. They present the set of holes at which we have in this direction varied the dose. And what we have seen, focusing now on this smaller dots, and also looking with another technique, which is atomic force microscopy, which we can also combine with single molecule localization microscopy, we see as well that on the location where the intensity that we see here is very low, we have a formation of hills. But if we leave this type of a material in the water for sufficiently long time, we have a transition from such type of hills to the holes. And what is the underlying mechanism of this is that basically our focused ion beam of xenons that interact with the material doesn't have a sufficient dose to remove a material, but just mechanically compromises the material being emerged in the water. This leads to this dissolution of a hexagonal boron nitride and formation of the holes. So we try to push the resolution of the xenon ion beam to be smaller and smaller, but unfortunately we could not reach the distances that are in the orders of a hopping length. Our next stage was then to go to the helium ion beam microscope, but unfortunately in Switzerland we have only one, which is in EMPA, and that one is constantly under repair, and we have not yet progressed with this project beyond the results that we have obtained with the xenon ion beam. So far I was telling you about the interaction of the water molecules with hexagonal boron nitride, which has been exfoliated and then treated either harshly with the focused ion beam of xenon in order to create these defective sites, or by oxygen plasma. But one interesting thing also happened when a student in the lab also tried to just do the control experiments in looking at non-treated hexagonal boron nitride. And when immersed in a water, non-treated hexagonal boron nitride doesn't display any fluorescence. However, if we place this into the organic liquid, we will see that we have seen a rise of the fluorescence. Just a little detour, and just to motivate people who might want to do this experiment at home, and maybe you have done this experiment if you are assembling the angstrom slits. So in the process of any building of the van der Waals heterostructures, one needs to exfoliate the 2D materials and position them on a substrate. And in the process of the cleaning, very often organic molecules are used, such as hot acetone or isopropanol. And when we have placed such a, and I guess this process has been done millions of times in the lab so far, because all solid-state devices actually have high-performing solid-state devices based on 2D materials. Heterostructures have on their top hexagonal boron nitride as an insulating layer. So this hexagonal boron nitride has been very often in a hot acetone as isopropanol, and to our luck, nobody looked at those samples under the microscope. And if you do that, what you would see very easily, so this is how Nathan phrased it, 5-minute sample that you can always make and always reuse. So this type of images can or movies can be produced very easily using, this case, pristine hexagonal boron nitride and organic liquids. So in this particular movie features interaction of the ethanol with native defects in hexagonal boron nitride. So until this point, this kind of a native defects in hexagonal boron nitride in the community that deals with the quantum emitters have been a bit overseen, and everybody was trying to do the this type of deterministic or strain-induced implementation of the defects, while the native defects has been actually observed with the scanning tunneling microscope. In this case, they are in order to obtain scanning tunneling microscopy images. On top of the hexagonal boron nitride, we have a graphene layer, but they are present here and also quite abundant. But nobody reported any optical activity. So what we see when we place when we image this fluorescent defects under the microscope, so after exposing to the lasers and after some time, and depending on intensity of the laser, this time of reaching the steady state can vary. So we enter in a steady state in which we have isolated emitters that are suitable for future analysis and use for single molecule localization analysis. So similarly as with our water, hexagonal boron nitride, which has been treated with the plasma, here again we can see the photons, and depending on the number of photons, we can localize the position of the defect and also read their emission spectra. So what we have done then in the lab, we have tried many different organic solvents, and as I said, for the water we have very little or no activity, and for organics this number of photons per micron square is really staggering compared to non-activity that we see in the water. So we have also seen that this phenomenon is universal. So examining the samples from Japan, US, or France. So really a very easy experiment. You can try it at home. What is exceptionally beautiful in this type of experiments is that really number of single particle trajectories that we can assemble from such movies also provides a rich environment for analysis, and we can have much higher statistics in this case than compared to the water type of the experiments. Regarding the proposed mechanism of the switching, we are still not really certain on what is actually happening. So we have definitely one type of a defect that interacts with the molecule. This interaction or maybe formation of the bond lowers locally the band gap in our semiconductor, and by interacting with the photons, we change the state of this complex, and then after some time, maybe likely molecule unbinds, and we re-enter in the same loop of activation, deactivation. So from the soft matter perspective, so this type of trajectories, now we can really analyze to the depth and establish that we have two types of states, so trapped state and the hopping state, very nicely. And we can as well determine diffusion coefficients. Looking a little bit more on the photon statistics of this type of experiments, we obtain a really high budget of photons, so comparable with the best organic dyes, so Alexa 647, and as well we have for some of them they are intermittent, but some of them are quite stable. And when we have such a quite stable stable emission from the emitters, we can also then perform more standard nanophotonic analysis. In this analysis, we can do polarization experiments, which we then recover a signature of the dipole emission, and we can also establish Henry-Brown twist experiment, in this case using two avalanche photodiodes and the beam splitter, and looking at the nature of the photons that are produced by these emitters. And in our case, we see clear signature of a single photon emission that can be reproduced in the different types of organic molecules, so in hexadecane or acetonitrile. Interestingly, so with just a simple change of organic type of solvent that we use, we can also influence our spectral characteristics. And this is very known in the fluorescence, and it is a part of it falls under umbrella of solvatochromism type of effects, where local dielectric environment influence the position of zero phonon line. But also we have seen in our spectral experiments that we also have shifts in phonon side bands that are also present in this spectra. So looking at the different types of the solvents, focusing on their zero phonon line and the phonon side band, we can see these shifts based on the dielectric constant and polarity of solvents. Recently, establishing also lifetime measurements on our setups, we can also measure the lifetimes as well as the function of a type of the solvent. And in the recent few months, we have transitioned from the using only two avalanche photodiodes to arrays of the avalanche photodiodes, so-called SPATs, in which we have in our disposal 512 by 512 avalanche photodiodes that all operate at the same time, allowing us to do lifetime measurements in wide field geometry. Interesting, and also I think for nanofluidics research, very important thing is that by adding a salt to these organic solvents, we can also see an influence on a number of emitters that we have per square micrometers. So by increasing the concentration of the ions, we see diminish the smaller and smaller number of optically active emitters. The crystal activity can be completely reinstated after thorough rinsing and leaving the system overnight. As well, with a spectral single molecule localization microscopy, we can also see the wavelength dependence for the mixtures. In a case of also what is interesting for nanofluidics perspective, we thought, okay, so this system is obviously a very nice sensor. Can we use it for also for flow measurements in a very a simple geometry that we also established. So we have placed our crystal and then sandwich it in a not a nanofluidic, but in this case, microfluidic environment. And by applying the flow, we can see again a stark a difference in the number of emitters per square meter when the flow is off or flow is on. This is even more striking if you look at the videos that are being used for reconstruction of these images. So at the beginning of the movie, the flow was off, and when we have turned the flow on, I hope you can observe as well a really stark increase in the number of optically active emitters. So where we are going with this? So idea was that in ultrafine confinements of the angstrom slits that this field uses extensively to study behavior of water and other solvents in the confinement. Our idea was that we use this optically active defects to probe local environment, exploiting the spectral shift as indicator of the confinement or changes in the electric environment that this confinement provides. So to build these devices, so we position hexagonal boron nitride on. So our collaborators in the Manchester position hexagonal boron nitride, pristine hexagonal boron nitride on the glass surface. They can use graphene spacers in order to form a volume or confinement level that the liquid will experience. And on top, we place a transparent mica so that imaging is possible, not only from bottom but also from the top. In our initial design, we are and initial experiments, we are still that I show. We measured from the bottom, and why we placed the mica on the top? Because it would be absolutely confusing to have as well hexagonal boron nitride on the top. But we will see for another instrument that we build, mica on the top is really a good choice of geometry. So what we can see, well, so we can see that the slits are filled with the that they are filled with the ethanol. So on an regular diffraction limited optical image, we see the region of a mask HBN and a region where they are actually nanoslits. And again, taking the spectra in the mask region or in a nanoslit or on a pristine hexagonal boron nitride, we can compare those spectra and look at the effect of the confinement. And do we see? And the question was like, will we see this spectral shift as a function of the size of the channel? And indeed, for both solvents, so acetonitrile and ethanol, we can see an influence of a confinement. So the spectral shift moves and indicates the level of confinement. We can also reconstruct the single particle tracks in these slits, and hopefully with this we can in the next experiments combine these experiments with measurements of electrical properties, or combining it also with the pressure, and that's something that we would like to do in the next phase. Another thing that we already made a progress was to influence maybe emitters by electrochemical environment using in-plane or out-of-plane application of the electrical field, and that's the work of Evelyn Meine. So she built the setup, and again, by applying here on ITO cover slip using a hexagonal boron nitride on the top and using the 3-electrode system, we can see an influence of applied in-plane electrical field on the number of optically active defects. This behavior is also can be repeated, and we see that emitters recover after the application of a voltage. So as I mentioned, so we are going in this direction so that we parallelize the measurements using for lifetime using the SPADs, and hopefully for also for single photon characterization using these time-gated SPAD arrays, and building the optofluidic setups, which currently also work. So we can measure and we can measure both the characteristics of the nanofluidic system optically and also using standard techniques. We are also moving to get results as well with the single molecule polarization, where we would study likely orientation of this organic molecule that interacts with the defects. And now shifting a bit gears, and also inspired by the work of Lydéric group, we thought of how to move also forward with the implementation of this nice ionic meristic devices into integrated logical circuits. So while most neuromorphic systems are based on nanoscale electronic devices, in the nature we rely mostly on ionic activity and also activity of neurotransmitters. So in electronics, so we have this meristor, which are passive terminal element with a programmable conductivity that depends on its previous history. So meristors can be, as we have seen, artificial equivalent of this biological synapses, and they can therefore store information. And in the field of artificial neural networks, the typical systems are using electrons as information carriers. And in biology, we have ions as information carriers. So as I mentioned, so the group of Lydéric Bocquet really here made a breakthrough in establishing that nanofluidic meristors that are based on bidimensional slits really can function in this electrochemical water window at voltages that are below 1 volt, and that can really display this meristic behavior. And as they are also bipolar meristors, they can enable implementation of a simple Hebbian learning algorithm and
realization of a real system, real biologically like meristic computing. So this behavior that has been seen in this carbon activated 2D channel devices was contributed to asymmetric entrances of the channel and slow interfacial diffusion, resulting in a minute scale cycles of accumulation and depletion of ions inside the channel. With this type of devices, Lydéric's group was able really to make this very fundamental breakthrough and to push the field forward. And now, knowing that this is possible, we have started to think like what could be improved on this system. In parallel, also there was a work based on a functionalized nanopipettes, but both systems, as we see, have one fundamental, let's say, difficulty, which makes it challenging to integrate them in real functioning networks. So it's very, very difficult to scale nanopipettes, or it's very, very difficult to scale up and also build the circuits of many of those systems to work together if one relies on nanochannels in a slits or nanochannels in activated carbons. In terms of performance, also like one could think of that one would need to also to improve the speed and also the on-off ratios. So what we kind of thought to be maybe an alternative, and that was a really serendipitous discovery which we stumbled upon is so we started in my group. We use normally wafer scale production of a silicon nitride membranes, and which we can on a wafer scale fabricate openings in a range of 50 to 100 nanometers, using this wafer scale nitride membranes, we position them in typical thermal evaporator, and under high pressure, low pressure, we evaporated palladium islands. Seeing this structure in a transmission electron microscope, immediately came the idea, why don't we cap these islands that form kind of meander-like or percolative paths for ions to form also confinement, and for that we used we started with the graphite, but also we used the other type of materials such as hexagonal boron nitride or mica. So what we quickly realized is that in this case, sorry, my presentation stopped responding. Sorry. Yeah. So what we quickly realized in this with this geometry that we have departed from the 0D, 1D, or 2D confinement to something new. Okay, so what we quickly realized is that we departed from something that is really different from the 0D to 1D or 2D confinement. And basically, what we have formed is a highly asymmetric channels, which we then termed as the hacks. So we have a combination of a giant aspect ratio between this entrances and the hole that is formed in a silicon nitride. So this ratio can be between 300 to 100-fold, depending on the size of deposited crystal on top of this channel. As I mentioned, in fabrication, all the steps until the deposition of the crystals can be done at the wafer scale. So that really allows that one can make really a lot of devices and characterize them also in different conditions very quickly, but also to start to dream to maybe combine them in a circuits. So similarly as in your work, Lydéric, we placed this chip in a nanofluidics system, and instead of applying regular DC voltages, we apply AC voltages. And what do we see? So upon application of the sinusoidal pattern, we see a signature of clear bipolar mermistive system with a special twist here, that there is this kind of abrupt switching at a specific specific state. So we can then define the system in an off or on state, depending when this switching occurs. And what we have seen is that we can improve basically a speed of operations. So we have a significant improvement in terms of the speeds. So we can go relatively faster, and also we can reach. So the performances are a bit better, and we can also reach larger on-off ratios. So between 8 to 20, again, depending on devices. sometimes it's really easy to correlate with the size of the crystal, but sometimes it's much more complicated to understand what is behind. So, besides exhibiting this permissive performance, so we see that when the applied voltage becomes positive, we have really this linear almost threshold and abrupt change in the conductance. So we have a really distinct off and on state. This is also similar to solid-state electrochemical metallization memory cells, and also not reported so far in nanofluidics. So this switching threshold enables non-intrusive access to the memory states and is beneficial for several also applications, and as well as we will see after understanding what is behind this switching, that we can implement them in logic circuits. So to understand the origin of this behavior, so we have performed experiment in which we have changed the amplitude of the voltage, and we see that the voltage at which the switching occurs is dependent of the bias amplitude. So therefore, it is not possible to define a clear voltage threshold, and this means that likely that we can maybe rule out many body effects and also a second bin effect as underlying mechanism. What we have here is likely something that is related to the accumulative charge. So in order to understand this, therefore, we have focused our attention to the performance of devices under different frequencies. So here, what we can see are current traces recorded at a different frequency, and they really highlight this continuous nature of ionic transport. So we see that the time required to reach the threshold increases monotonously with decreasing frequency, showing that the switching is not only related to the time spent at the positive voltages, but likely to the charge. And if we if we also then look at the amount of the charge as a function of the frequency, we see that this charge is preserved and not dependent on the frequency. So that led us to believe that when a given amount of ions has flown to the device, we have occurrence of the switching. And now trying to understand this a little bit better from building a simple toy model. So in this toy model, we will just peer into the kind of a look at the entrance polarization effects and see that really we have a system where we have a high polarization, concentration polarization effects that are really dependent on geometry. So to really rationalize this observed charge threshold, we have developed a theoretical framework based on extended space charges. So these extended space charges need to kind of they are accumulated at the surface, and at the beginning, our device really doesn't sense them, and we need to move them, and that only happens when we reach this charge thresholds. So the source of this highly charged channel is due to the entrances and this high asymmetry, and also surface charge that is present on the graphite. Because if we move to, for example, to the mica, we don't have this effect anymore. For a bit less charged systems such as hexagonal boron nitride, we recapitulate the behavior, but as I mentioned, it's really important to have high asymmetry. So for ions, so that we have from this side when they enter in a system, it's completely different if they are entering from this side. So that is really setting up conditions for our charge threshold, and as well operation of the device. But this simple toy model allow us really to compare and to see when this threshold is reached and when it can be reached and in which condition it can be reached. So we now know that, and also from the experimental data, we see that in low molarity situations of 100 millimolar, we cannot reach this charge threshold. It is also very important to have a high asymmetry. The lower asymmetry is, this behavior is smaller and smaller. So we now, with the model in hand and also some understanding of how the devices are operating, we started to think of like how to exploit this switching behavior, and also to build the logic circuits. In order to do that, we team up with the colleagues from the LANES, the laboratory that builds memoristic circuits on using the electronics. And our idea is that for building the logic circuit using two electrolytic memristors, the easiest path would be to go towards implementation of a so-called IMP logic gate. And that is the material implication gate. This type of gate was proposed back a long time ago, but implemented recently and demonstrated in 2010 by Borghetti using two electronics-based devices. So we basically mimicked really everything that was previously done with electrons. So having instead of two electronic memristors, two nanofluidic memristors. So one which we call the VP and one which we called a VQ. So now instead of being wired by the wires, they are wired by the water ions, and in between them we still have electronic resistor, which plays a big role because we will need to adapt its resistance based on the logic functions that we want to implement. So to build this type of the logic, as I mentioned, this IMP type of a logic device. Oh God, I don't know again.
Actually, Aleksandra, maybe maybe you could go to the conclusion if you don't mind.
Yes, yeah. I will then skip to the conclusion. So we could build this IMP logic based nanofluidic circuitry. Yeah, sorry.
Don't worry. So maybe it's just simple a good time to make the conclusion. I think.
So basically, we recapitulated everything that what has been done in electronics using ions as information carriers. So I wanted a little bit to no, this is wrong. So we have successfully implemented the IMP using two hacks. Recapitulating everything in a logic table. So based on the conditional switching of the P prime Q prime to the P and the Q. So if we go back to the logic table. So here, really, the output states are really dependent on the input states, and the very important is in which state is our primary device, so P. So is it on or off? And then upon implication of through the implication of the set and the threshold voltage, we can manipulate the output states P prime and the Q prime. And indeed, that is the case. And basically, I would just like to finish with the working conclusions. So we have stability for the highly asymmetric channels, scalability, speed, and improved conductance ratios. We have this unique switching behavior in hacks. We could build the logic circuits. We could also simulate those logic circuits. And we see that these geometrical effects and interplay between charged surfaces of the graphene of a 0.1 coulomb per meter square really play a big role, and that we should focus our future efforts on connecting more hacks and also use water channels to create fully liquid circuits. And with this, I would like to thank you for your attention.
Thanks a lot.